Okay, so in this video, I'm going to talk about how to take a lot of the important old definitions that we've made about convergence of sequences, Cauchy sequences, and completeness, and sort of modify them slightly to get new definitions that apply to arbitrary metric spaces, okay? So the key here is, so we're going to take definitions for R and turn them into definitions for metric spaces. All right, so any metric space. So we can talk about sequences of points in an arbitrary metric space, and you know, completeness for arbitrary metric spaces, and so on. So I'm just going to, you know, the key. All right, the key is in each definition, replace, oops. Well, okay, it's not this simple. Here's the idea. It's sort of a vague idea. In each definition, replace, you know, instances of, you know, B minus A, or, you know, similar things with the distance function for our metric space, right? So here, for example, well, okay, I'll just give definition 13.2. So a sequence Sn in a metric space converges. Oops. So this one doesn't look like what I was just describing, but I'll tell you why. Converges if, or converges to, let's say, to S in the metric space if the limit of the distance from Sn to S is equal to 0. So this doesn't look at first glance like, you know, an example of what I just said, but, you know, another, so the definition of the limit of the distance going to 0, right? So let's just on the side here, equivalently, you could say for all epsilon greater than 0, there exists an n such that for all n greater than n, we have the distance from Sn to S is less than epsilon, right? Instead of the absolute value of Sn minus S, because remember, if Sn is coming from a metric space, we don't even know if it's possible to add or subtract elements of the metric space S. S might be a set where addition and subtraction don't make sense, right? But so we can get around that problem by just using the distance function here. But this is literally just like a translation of what it means by definition for this limit to be 0. So the only reason they say it this way is just because it's like more compact than writing this whole thing out. But then when they do the definition of Cauchy sequences, you know, it's really this process here where you see they just replace Sn minus Sm with the distance from Sn to Sm. So Sn is Cauchy if for all epsilon greater than 0, there exists an n such that for all n and m greater than n, we have that the distance from Sn to Sm is less than epsilon, okay? So it's literally the same definition, but with the absolute value of the difference replaced by this distance concept. Now, lastly, S is complete, and this one bears a little bit more discussion, and they do a fine job of explaining this in the book too. S is complete if all Cauchy sequences in S converge to an element of S. So this actually is kind of like misleading wording here, or maybe there's sort of a red herring here, okay, which is there's a technical thing of like, okay, you know, you can have a space, a metric space, which can also be considered a subset of another metric space, right? So let's say, for example, the rational numbers. The rational numbers with the normal metric of the absolute value of the difference, right? The rational numbers form a metric space, and they are a subspace of the real numbers. And so the point is that, you know, the rational numbers are not complete in this sense because there are Cauchy sequences of rational numbers which don't converge to a rational number, right? But actually, technically speaking, it makes more sense just to say that in Q, in the rational numbers as a metric space, those Cauchy sequences simply don't converge at all, okay? Even though those sequences converge to a real number, maybe, if you think of Q as a subset of R, there are sequences in Q which converge to something in R outside of Q, right? But that's only when you're thinking of the sequence as existing in R. So you say that the sequence converges in R, but it does not converge in Q, okay? It simply doesn't converge in Q. So like if you drop the context of Q being a subset of R, then there are a lot of sequences in Q which just, there are a lot of Cauchy sequences in Q that just don't converge whatsoever. And that's because their limit, quote unquote, lies outside of R, even though that's like not really the right way to phrase that, okay? There's like a really minor sort of technical distinction here, but I think it's kind of, it bears mentioning. So let me just talk a little bit more about completeness here. So and notice how they write like pairs like this. So the metric space is sort of technically the pair of the set and the distance function. But you'll also notice that like a lot of the time, instead of writing out the whole pair, we'll talk about the metric space and just refer to it as S, even though S is technically the underlying set. If it's obvious from context what the distance function on S is supposed to be, we'll usually just refer to a metric space as just S. So if I refer to the metric space R, for instance, I'm talking about R with the Euclidean distance function, or like R2, right? I'm talking about the plane with the Euclidean distance function, R3, so on, right? Any, like RK, if I talk about RK as a metric space, it's assumed that the distance function is the Euclidean function, unless otherwise specified. But technically, the metric space, you know, to specify a metric space, you have to specify the set and the distance function, right? So the thing about completeness in metric spaces, right, is that, or rather in R versus, you know, in metric spaces, right, is that like for R, we said R was complete because every bounded or bounded above, or, you know, bounded above set has a supremum. It would have been the same if instead we said the completeness axiom of R was that all Cauchy sequences in R converge. Okay, so the problem is, so basically, if you declare for the real numbers, if you take it as axiomatic that all Cauchy sequences in R converge, then you can actually prove from that. So the Cauchy sequence convergence you can prove from that that all sets bounded above have a supremum. You can actually prove this from this one. In fact, they're equivalent to each other. So Cauchy sequence, this is Cauchy sequences in R. Okay, this is of course also in R. So the only reason we had to change the definition of completeness here for arbitrary metric spaces is just because most metric spaces don't have a concept of ordering on them. Remember, like R is special because it has this concept. So R has the concept of ordering, right? Which does not exist for other metric spaces, at least not in any sort of sensible or natural way. I mean, you can define arbitrary orders on any set if you want, but they don't have a nice ordering structure which agrees with the rest of the topological structure on those other metric spaces. So like R2, there's no natural way to order the points in R2, right? Or in R3, you can't order those points in a natural way. I mean, yeah. So yeah, just take my word for it that the ordering structure on R is very special, and that's what lets us define completeness in terms of the supremum instead of in terms of Cauchy sequences. But we could have defined it in terms of Cauchy sequences if we wanted to, and nothing else would have changed. We would have just been going in a different direction here, where we would be proving that all sets have a supremum from the fact that Cauchy sequences converge instead of vice versa, which is what we ended up doing for this class. So that's it for the sort of adapting the definitions. Those are the three main definitions we wanted to adapt so far for metric spaces. So in the next one, I will show that I'll prove a basic theorem about convergence in RK.